frequency shifting. This is what we're doing now. We were talking about modulation, so the simplest scheme of modulation is amplitude modulation, and we use frequency shifting for that. So we know that if x of n has the transform x of omega, then x of n minus big N has the transform x of omega e to the minus j n omega, right? Shift in time domain, multiplication by an exponential in frequency domain. Something very similar happens when we have a multiplication in time domain. So, and let's go on here. X of n times e to the minus j. In the table, is it with minus? No, it's with j. J, some frequency, omega 0, n is x of omega. Now it's plus or minus. Omega minus omega 0. We're in the continuous time table. This will work better for us. Minus. So instead of 0, it's calling it omega c. Omega c and omega c. So what? What do we use this for? Suppose you have some signal. It can be, for instance, a voice signal, sound signal. And it's centered around 0. Okay, it's somewhere here. It goes until a maximum frequency. We can, let's work with hertz. This will be more interesting. It goes until 10 kilohertz. You want to transmit it with a radio. And your radio can transmit signals which are centered around 100 kilohertz. So you cannot transmit this with your radio. You have to shift this spectrum here and transmit it, and then in the receiver you shift it back to 0. The way we can do it is to multiply the time domain signal by complex exponential. Do complex exponential really exist? Not really, right? So what do we have which is close to a complex exponential? A cosine. A cosine is a good surrogate for the complex exponential. In practice, we multiply by cosines. So if we do this, we shift the spectrum here. Okay, if we multiply by a cosine, x of n times some cosine of omega c n. What's this? This can be written as x of n times half e to the j omega c n plus e to the minus j omega c n. So we have two complex exponentials when we have a cosine. So what will happen is we're multiplying by both of them. We will have x of n e to the j omega c n plus half here, half x of n e to the minus j omega c n. The Fourier transform this. Let's work in hertz. We will have x of half x of omega minus omega c plus half x of omega plus omega c. We'll have two copies of it. One shifted omega c to the right, one to the left. And then we can transmit it with our system that only transmits things within this range. There's an example here. First, I define a signal. This is my signal. I'm already plotting it in the time domain in seconds here, assuming 1,000 hertz of frequency sample rate. Notice that this signal has an infinite spectrum because it has these discontinuities. So the spectrum is very large. So in order to do this and make this work, let's create a frequency limited version of this signal. Here I did the Fourier transform. Here I'm creating the low pass version where I erase any frequency component above 50 hertz. So the signal will stop here. This is the low pass spectrum. And then I do the inverse Fourier transform. Where is it? Here, FFT, IFFT. This is my low pass version, my low frequency version of the original signal. So this is the time domain signal that we're going to modulate. Actually, this signal will modulate a carrier wave. So this signal contains the information that I want to transmit. Now I will do this multiplication. I will multiply by a cosine with 150 hertz. So I might find here one copy of it in minus 150 and another one plus 150, another one in minus 150. So here's the carrier. I will plot it in time domain and in frequency domain. In time domain, I have to do a little zoom here because if I don't,
I don't think we from electrical engineering, we don't have this like telecommunication background. The carrier that you call, this carrier signal, what is it?
So we want to shift. This is our original signal. Say this is the spectrum of this guy here, which I will transmit. I have to multiply it by something to shift it. This signal that I'm multiplying it, with which I'm multiplying it, is called the carrier.
Okay, the cosine is the carrier.
The cosine is the carrier. The C also stands for carrier here. And that's because it carries the signal with it. So, carrier, here it is. Let's do the zoom here again. And here's the spectrum, the discrete time Fourier spectrum of my carrier. We know that the spectrum of a cosine is a pair of impulses in the frequency domain. So what I'm doing actually is I'm exploring another property, which is multiplication in time domain means convolution in frequency domain. So I have a cosine as a carrier that I'm multiplying my signal with. So in the frequency domain, I take the spectrum and I convolve it, sorry. Multiplication here, convolution here. I convolve it. So if I do the convolution of my spectrum with this, I just shift a copy of it to the left. With this, I just shift a copy of it to the right. So here's the carrier. Now we're doing the modulation. We're taking the signal and we're modulating the amplitude of the carrier with the amplitude of the signal. So modulation means multiplication. So here it is. My low-pass signal multiplied by the carrier will create this X modulated, which is here. Here's the carrier multiplying the signal. Here's the spectrum. This is what we expected. The original spectrum, which is this one, with two copies, one shifted to the right, one shifted to the left. Now I can transmit it. Here it's 150 hertz, right? Here I mentioned 100,000, but the principle is the same. Once I transmit it, someone receives it. This someone has to shift it back to what we call a band-based signal. Baseband, a baseband signal. This is a baseband signal. So the receiver has to shift it back to the baseband, while this is the modulated signal. So how to shift back the baseband? When I multiply by the carrier, I create one copy of this here, one copy of this here. Right? This is the modulated signal. We can call it M of omega. How to shift back. If I multiply again by the carrier, then this guy will be convolved with both impulses. So I will create one copy of it here, one here, right? One here, another here with twice the frequency, the original shifting frequency. Same for this one. One here, I will have two of them here, one here with twice the frequency. Do we have this here? Demodulated signal, demodulated signal, X demod. Modulated times C. So here's X modulated, demodulated, okay. I have already twice the frequency. Here's 150, here's 300. But why don't I see this copy here? Sorry. I know why. Because of this phase. I put this here to show that this will prevent the system from working. Now, it has some relation to what we were talking about. You need to know the phase of the carrier that comes from the emitter. So here it is, the demodulated signal. Here's the original, the demodulated signal, and here's the copies with twice the shift. So I still don't have the original signal, right? I have it here, a copy of it, but there are those other two copies. What can I do now to get rid of those copies? Low pass filter. So I'm filtering here anything which is above 60 hertz is being killed. Then let's do this again. Okay, here's the resulting spectrum. Here's the resulting time domain signal. I believe it will have half the original amplitude. It's going up to 30 here, and the original one was, yes, 60. Why? Because there is this division by 2 pi here, while the transform of the cosine has pi in the equation. If we go to the table, we can see it. Cosine. Here, pi. Why is this sum here? Because the spectrum is periodic. So the author has to put this sum here to make it clear that it repeats every 2 pi radians per sample. So this pi with that over 2 pi, these guys have half the amplitude, then half again, 1/4, 1/4 times 2, half. So if we want a copy of the original signal with the same amplitude, we have to multiply by 2. But this is the ideal case where there aren't losses in the channel and so on. So this is amplitude modulation, which is the simplest case of modulation. The other ones are very similar. They all involve shifting the signal in the spectrum. Another thing that we can do is we can do multiplexing. This is our modulated signal, we can sum it with some other modulated signal. Here, for instance, this was modulated by a certain frequency, this one by another frequency, this one by another frequency. Then before demodulation, we have to band pass the signal, and we get rid of what we don't want, and then we do the demodulation. And we can band pass here. And this is what you're going to do in the activity. I have to translate it to English because I only have this activity in Portuguese, but let's take a look. Classroom. In this activity, you will work with actual audio signals. Demodulation of modulated signals. There's a file which contains two signals. One of them is modulated with 10 kilohertz, the other one with 20 kilohertz. So you have to, this is the file. You have to band pass the first one, demodulate, and play it. Band pass the second one, demodulate, and play it. You can use, as an example of how to read a wave file, how to play it, and so on, you can use this code from last class, ideal filters. Here I show how to read a wave file, how to save a wave file in the in the virtual file system here. To upload, you upload to here. You won't need to upload. I will adapt this to use gdown to download the file. How to play, you have some examples of how to play the signals. Sorry. This is from last class, right? You can use those examples to band pass, high pass, low pass, play and modulate and demodulate the signals. Okay, this is what we had to discuss about the property of time domain multiplication, which provides us with amplitude modulation.